All right, so good. Let me mute. Right, so put this on full screen. Good. So when we ended last time, we started this looking at this question, and this led us to the discussions of the topic that was at hand, which was stability. And what we were discussing specifically was something called the Routh-Hurwitz stability criterion, which in summary was a way of determining if a system was stable without having to solve for the poles of the system. Remember what we had said, and we have discussed on a number of occasions before, was that if the if the poles of the system are located in the left-hand side of the S-plane, that it will be stable. But if it goes across into the right-hand side of the S-plane, that the system tends to become unstable. And the more general sort of consideration that you have to look at when you're doing things like control systems is the sort of problem that you're seeing here up on the screen, where you have a feedback system. The main system has a transfer function of some form. The feedback part has another transfer function, but associated with the feedback part is a gain, right? So this is some gain, some feedback gain. Let me just put that here. Right? When you evaluate these systems, because it's negative feedback, remember it's a 1 plus GH. Of course, these are all functions of S. But depending on the value of right, and then in summary, what we saw is that this bit here, the 1 plus GH, right? If you set that equal to 0 and solve for the roots, these were the poles of the closed loop transfer function. And this is what determined whether the system was stable or not, right? You want the poles to remain in the left-hand side of the S-plane. What happens in a lot of control systems is depending on the feedback gain. Sometimes you can also have a gain appear in the plant, right? So when you eventually simplify it, sometimes the simplest form, this would be what they call the plant, and this would be like the controller. Right, just in general terms, they're going to meet this. Let me make that N a little bit better. And right, but in general, this is what you're going to meet. Sometimes there's a gain up here as well too. There may be a gain factor up here as well. And what happens is that depending on that value of gain, the poles of this system, which originally when designed, the poles may be nicely located in the left-hand side of the S-plane. As you vary the gain, one or more of the poles start to head in this direction. Right? So it may be here, and then all of a sudden now, depending on the value of K, the poles now land up on the right-hand side, and the system becomes unstable. So the issue in controls, for instance, is what is the range of values for K before this happens? In other words, what are the values of K that I can use that will make sure that all of the poles of the system remain in the left-hand side plane? That is easy if this thing just has a couple of poles in it. Most systems do not. So you have 3, 4, 5, 6, 7 poles you could be contending with. So solving the poles for each value of K is not going to be an issue. All right, if you have things like MATLAB, it is possible there are polynomial techniques for solving roots of polynomials and so on, but we're not interested in that. What we are interested in actually is what happens if the poles, if the gain shift. Half a second. So the alternative that we have, instead of having to solve the poles, would be to find a technique where we can actually see what the behavior of the system looks like without having to actually go and solve the poles. And that's where the technique that we just started to discuss last time comes about. The technique is called the Wouter-Hurwitz criterion, right? So, and let me just so keep this, and let me share that now. So when we started, right? So the technique was a tabulation technique. And before I put it back up, you remember what happens is that you have the technique, you get that equation. This comes from the G over 1 plus GH, right? This bit, if you set that equal to 0, it is what we call the characteristic equation of the transfer function. And we tabulate this now depending on the order of the poles. Sorry, the order of the system. So if this was something like s to the power 4 plus 17s cubed plus 9s squared minus 3s minus 15, for instance, the tabulation method was that we use a lot of paper for this. You look at the highest order first and you draw a row s to the power 4. And what you're going to do is to draw a row, and you're going to put the power, you're going to put the coefficients of s to the power 4, which is 1. The coefficient of, you go down 2, so this will be s to the n, sn minus 2, sn minus n minus 4. N happen to be whatever this is, right? So this is the n for this particular row. So if Sn, so Sn minus 2 would be 9, and Sn minus 4, which is s to the power 0, will be minus 15. Make sure and copy it correct. And the next row that we go is s cubed, which is the missing lot. So n for this row is 3. So we look at the coefficient for s cubed, which is 17, s to the power 1, which is minus 3. And then, of course, we have nothing here. We could leave this blank, or you could put it 0. And then what we have to do from now on is to calculate what the coefficients are for s squared. Right, what the coefficients are for s squared, s to the power 1, and s to the power 0. Right? So we will be doing all of that. And I said you use a lot of paper. And of course, the technique to do it, as we said, is similar to what you use when you are evaluating a determinant. It's just that the order is reversed. So here, if you're looking at this particular cell here, now to fill in the table, you look at the 2 rows immediately above. So this is the s squared row here. We're going to look at the s4 and the s cubed, and we start always with these 2 values above here. So this value here is going to be 17 by 9 minus 1 by minus 3 divided by 17, and you put whatever that value is. Okay, here is going to be 17 by minus 15 minus 1 by 0 divided by 17, and you put this value b. And so you keep, and what I suggested is that you completed 1 row at a time and copy over the table. Otherwise, there's a tendency to make mistakes. And I made one when we were reviewing the December paper, because of that, trying to do it on the screen and not having enough paper and so on. So once you do that, you copy it over, and then you go to the next row. So the next row after that would be the s to the power 1 row. And then here you're going to use the 2 rows immediately above. So you're going to use the S cubed and S square rule. So here is going to be A by minus 3 minus 7 by B divided by A, and you get that. And then this one is going to be A by 0 minus 7 by 0. Remember, this is a 0 here over A. So this row is going to be 0. And then the last row to be evaluated, which is this one here now. You look at the 2 rows above, which will be S squared and S1. So here will be C by B minus A by 0 divided by C, which turns out to be B. Okay? As it turns out in this particular case. So once you do that now, and you haven't made any mistakes, what the criterion tells us now is that we look into this column. We look at the first column, right? So you examine, where's my, right? You examine first column of the completed table and look at the signs. Right, so you look at this, you're looking at the signs now, right? You're being a prophet. So you're looking at the signs and you're trying to see, first off, any negative signs. If there's a negative sign in any of these values, so if, well, 1 and 17 is there, if A was negative, C was negative, or B was negative, then the system is unstable, right? So that is straight off your answer right there for, is this system stable or not? You see a negative sign inside of there. Once you see a negative sign, the system is stable, unstable, okay? The next thing now is that from the signs now, we could still get some other information. You could find out how many poles. So if it's unstable, it means that there are poles in the right-hand plane. The other part now is that if you look at the number of sign changes, then you can tell how many poles are in the right-hand plane, which is another useful feature to get. So you're getting that information without solving the 4 poles of this. This is a 4th-order system, so this has 4 poles, right? So you look here, and let's say this was a minus sign. Then you look at the number of sign changes. So from here to here is no sign change. Here to here is no sign change. A to minus C is 1 sign change, and C to B is 1 sign change. So if I had a minus sign here, I have 2 sign changes, which means there are 2 poles in the right-hand side of the S-plane, right? So you get all of that information by without having to solve that characteristic equation and find out how the poles, what the actual values of the poles are. Okay, so that was where we ended in summary. So this is how the technique works. And now what we're doing today now is that there are a couple of exceptions to the technique. In that, first off, what happens if somewhere inside of here, one of these values here is 0. And then the other thing is what happens if an entire row turns out to be 0 for you. Okay? All right, so let's look at that. Everybody following? Let me just discard this. All right, so everybody following what we've done so far. All right, the recording was there, and this was again a sort of summary of that. So we all right with that? Yeah? Yeah, no, maybe? Give me some feedback.
Yes, sir.
All right, great. As I said, I have to watch another monitor here, so it's not always possible for me to see if you put something in the chat. Okay, so let's look at this one now. This particular characteristic equation is very simple, so it's for illustrative purposes. If you tabulate it, you have the s cubed rho, which of course s cubed means n is 3, so you put s to the n and sn minus 2, which will be 3 and 1, and s squared will be 2 and 2. If you tabulate that, then this value here is going to be 0. 2 minus 1 minus 2, 1 minus 2 divided by 2 is 0. So if you do that, if you fill in the row now, then you get this value here, and then we're stuck. We can't go beyond that because at this point in time, we can't determine what happens in the row 0 anyway. So this now brings us to one of the two special cases that I mentioned. One where the first row entry is 0, and the other one where the entire row is 0. Okay, now remember from last time what we said is that for the system to be stable, all the elements of the first column must be strictly strictly positive. Strictly positive means that they have to be greater than 0, right? So from the time you see a 0 inside of here, this system is marginally stable. Right, and you'll see where the roots lie in a little while. What happens in that case now is that we make a little assumption. If the first value in a column now is 0, then what we do is to see, in order for us to complete the rest of the table, let's see what happens. What we do is that instead of the 0, we let this be a very small number. E is greater than 0. So a small positive number. A small positive number. Remember, we want everybody in here to be positive. So let's see if we increase this from 0 to a very small positive number, and let's try and complete the rest of the table and see what happens. So if this is a small positive number, this one will be epsilon, well, 2 epsilon, this is 0, minus 0 divided by epsilon. So here will be 2, right? So if I assume that that cell, let's increase this and say instead of 0, let's make it very slightly positive and complete the rest of the table and see what happens. Then at this point in time now, you have a system, well, a completed table looking like this. So you ask yourself, how many sign changes? We know epsilon is positive, so we have 0 sign changes. So if the system is like this with epsilon being just positive, then the system is almost stable. That particular behavior means actually that what happens is that, remember we're dealing with the S-plane here, which is the sigma part, j omega. So this is the S-plane. We want all the roots, as we say, on this side. From the time you get us, when you tabulate the outer table and you get a single 0 in any of these cells here in the first column, what that means is that somewhere inside of here, the system has a pair of imaginary roots, purely imaginary roots that are located exactly on the j omega axis. You remember all roots have a sigma plus j omega part to them. The 0 in that cell is going to tell you that you're going to have a pole where the j omega, where the sigma part is 0. So the pole is located exactly on the j omega axis. So it's not really on the right-hand side. but is about as close as it could get. This kind of thing is what we call marginal stability, and the system, that kind of system responds with oscillation. So if you were to put a step response on that system, if this was a step input to a system like that, the output of the system is going to look like this. Instead of that, the output is going to do this kind of thing and then settle down, right? In most types of systems, you do not want that kind of behavior. Just think about it. If this is a motor control, for argument's sake, and the step change was to change the speed from 50 RPM to 100 RPM, you don't want it, if this is the 100 RPM here, you don't want it going up to 120, let's say, and down to 80, and then oscillating, and then after, 5 seconds, 4 seconds, and that kind of thing, it now settles down to what you want. Or if this is a robot, and you're moving, the robot is moving material, it's like a assembly robot, for instance, and it's taking components from one part straight to another, a heavy component. You don't want it moving, and then instead of dropping it where it's supposed to drop it, now it overshoots, and then it comes back, and then eventually wobbles around and settles down to something. All right. So this is special case number 2. If you have a 0 in a cell in the first column, then that indicates that the system is marginally unstable, right? Or marginally stable, sorry, I should say, right? Marginally stable, marginally unstable, probably the same thing. So I could, we will accept that, right? So you could, if I ask you a question and you tell me it's marginally unstable, I will accept that as well. All right. So, well, here's the, when you get the graphic, you'll actually see what the actual poles look like if you were to solve it. All right. So let me see. If you do that, right? So the actual poles for the system, if you were to solve it, it's a third order system, so it's relatively easy to solve. 2 of the poles are at S equal to plus or minus G, all right, which are right on the 0 axis, the sigma equals 0 axis here. So what about this one now? Here's a 5th order one now, and you want to find out again if there are any poles in the right-hand plane. If you tabulate this now, then the next time you fill it in, and you could verify this now, you're going to get this entire column. This is also a 0, but this is understood. But you now have a situation where you not only have a 0 in the first cell, but the entire row is 0. All right? What do we do? Because we now can't fill in these 2 inside of here. All right? So what we do now is a little bit of calculus. We look at if the first element and all the remaining elements of that row are 0, what we do is that we form a new polynomial using the row immediately above. So the S cubed row is 0. We look at the row above that we have, and we form something called the auxiliary polynomial. So this is Sn here, n is 4. So that row will be 2s to the power 4. This will be s squared plus 48s minus 50. Right? 48s squared minus 50. So you form a new polynomial in that row. And then what we do now, this is all part of the polynomial theory that this is based on. We're not interested in the technique. What we do now is to find the derivative of this. Notice if I find dpds, that is going to be a polynomial of order 3. If I take the derivative of a 4th order polynomial, I'm going to get a 3rd order polynomial, which is going to help me. Remember my table, I have S5 here, I have S4. S cubed is a row that has all the zeros. So by using the auxiliary polynomial here, I'm going to get a new S cubed row that will not have zeros in them. So the differential of that, of course, is if you find dPds, this is 8s cubed plus 96s, right? Of course, this will drop out. Notice the coefficients now for the S cubed row will be 8 and 96. And then you try to complete the rest of the table here, right? So you go on and you complete everything inside of here. And then you look at the sign changes again. According to this thing, if you, first off, you complete the table. If you encounter another row 0, you do the same thing. If you encounter a single cell being 0, right, you replace it with a small positive number. Yeah? And then you complete the table, and then you go back and check the sign changes. This has how many sign changes? If you look, you go row to row, no sign change, no sign change, no sign change, no sign change, one sign change, right? So this has one sign change to it. Right? So therefore, according to this thing, there's at least one pole in this system that is across on the right-hand side. If you were to solve it now, what it is going to tell you, this, well, first off, the system is unstable, and the zeros in the table indicate, first off, that we have a pair of real roots, but one of the real roots, remember, all the roots are sigma plus j omega. One of them, the sigma is positive, so it goes across on the right-hand side. Remember, this is the right-hand side here. And then the one, that first zero also indicated that we have two poles on the right on the j omega axis. Right? So the system is unstable, right? You have no question about it being stable or unstable, right? Give me a second, please. Right? So, so you have the answers again without having to solve the 5 poles. If you did solve it using something like MATLAB or sometimes your calculator could probably do this for you as well, you will get this pole, which is all well and good, right? So this one is all right. This plus or minus 1, right? The minus 1 part, sorry, the plus 1 part, if s equal plus 1, that is of course here, which is an issue, right? And then the complex conjugate ones with no real part, that also is an issue. Okay, so all of that information you're now able to decipher. First off, is the system stable, right? Which is the crux of the matter. And how many poles lie in various places on the S-plane without solving the equation. You never had to get to this. You never were required to do this, right? And that now, having done that now, it brings us to the sort of interesting part. As I said, this is the more likely application that you're going to meet when you do controls and so on, is that in the characteristic equation, because of the feedback or the gain parts of the system, there is a value that you could set by a controller. And depending on the value now, this will tell you if the system, you know what is the range of values. So it's kind of like the volume control on an amplifier. If you have a big amplifier and you have a small loudspeaker on it, you can't set the volume beyond a certain amount, otherwise you'll blow the speaker. So this is the sort of thing. At some point in time, depending on the value of K, the poles of this system, right? If you look at the poles, maybe with K equal to 2, all the poles are here. It's a 3-pole system. So let's say we have one simple pole and 2 complex poles. As you vary K, these poles going to head across towards this side, all of them, right? And at some value of K, this pole now and this one, if they're complex conjugate, they're going to move together. So at some point in time, they're going to land up here. And then at some little point in time, again, as you vary K, you're going to land up on the right-hand side, and the system will go unstable. So how do I determine what is the value of K that will make that happen? So we go to the same Route-Hurwitz criteria, and we fill in the table exactly as we do, except that K is now a variable inside of there. So this, you fill in the S cubed and the S squared rows. So 1 and 4 and 2 and K is now here. This cell here, of course, is 4 by 2 minus K by 1, or 1 by K divided by 2. So that's 8 minus K over 2. And then this row here, I keep saying row, this cell here is this by K minus 2 by 0 divided by this. So this is in fact K here. So what is the value of this that will make this system unstable? What we need, remember, what does the criteria say for stability? Everybody in this column has to be positive, strictly positive, i.e. greater than 0. All right? So you go cell by cell now. So let's look at S1. If I tell you 8 minus K over 2 has to be greater than 0, what is K? If I tell you 8 minus 2 over K has to be greater than 0, what is the inequality related to K? Okay, somebody said less than 8. Let's see. So this means if I go, the next step will be 8 minus K is greater than 0, right? Or 8 is greater than K, or if I swap it wrong, K has to be less than 8, right? So that is what this row is giving me, this particular, that cell, sorry, is giving me that particular answer. The other cell now, here, this now, K has to be greater than 0 for it to be positive. So if K has to be greater than 0, you look at that, let's draw a little number line now. So we have, this is K here. So this first answer is telling me this is 8. So for stability, K has to be, this is K less than 8, this is 8. And this one is K greater than 0. K greater than 0. So therefore, what is the range of values for that system to be stable? The only way that system you could satisfy 2 things, right? K has to be less than 8. It also has to be greater than 0. So the only place where that is satisfied is if K is less than 8 and greater than 0. Yeah? Everybody seeing that? Yeah? No, maybe? Yes?
Yes, sir. We've seen.
Nice. Good. So that now, remember, we haven't We can't solve this. You can't find the roots of this. The only way to find the roots of that would be to say, okay, let k equal to 1 and solve this. Let k equal to 2 and solve that. Let k equal -3 and solve that. They're not going to help you get this range. That's a trial and error method. Okay, but by using the Hurwitz technique now, we're now able to see what the range of values to make the system stable. So what would make it, let me ask you, what values would make k, sorry, what values of k would make the system unstable? What values of k would make the system unstable?
So you just have to flip the signs because, yeah.
Well, except that it wouldn't quite work in an inequality, but right, this will, as soon as k goes greater than 8, right, greater than or equal to 8, in fact, remember we have marginal stability here. So if k goes greater than or equal to 8, or k less than or equal to 0, right? You then you are as you say, somebody flip the sign, but remember the equal part now, right? So if you put k equal to 8 here, you get a 0 here. Remember that is a marginal stability where it oscillates, right? If you make k is 0, you have here, and if k is less than 0, of course, you have a negative sign immediately here. So the system immediately becomes unstable. All right. So you can look at the question in either way, and you will see the past paper questions asked that. What is the range of values for k that makes it stable or unstable? All right. And here we have it here. So it brings you back down to this kind of question, which is similar to what the past paper question looks like. What is the range of values of k that will drive this particular system unstable? So the first thing you're going to have to do here, right? This is G and this is H. So you're going to have to find the G over 1 plus GH, right? This now is your characteristic equation. So you tabulate that now, whatever that is, and then you're going to have k in it. So you're going to have some entries in the table with some function of k in the cells, f1k, and so on as you go along. So this is second and thing. So this will be a third order system. So you'll have a s cubed, a s squared, a s naught, right? And then for each of these particular values now, you do exactly what we did before. And then you combine all of the results now to say when the system is stable, and therefore the conjugate of that, if you like, will be when the system is unstable. Yeah. Of course, you have to make sure not make any mistakes in here. Generally, when I'm marking a question looking like this, one, I want to make sure that you simplify it correctly so that you start with the correct equation here, right? If you get the wrong equation here, you will lose, let's say this is a 10-mark part, you would probably lose about, normally it's about 2 marks to simplify, 2 to 3 marks to simplify that. So you'll probably lose the 2 marks for getting the wrong equation. But then if everything else is correct, I will watch what you did from this equation and see. And if you use the incorrect equation and you got the, based on your equation, you got the correct answers, right? It just is more work for me, but you will get the full marks for the rest of the problem. Of course, if you make errors in the table and all that kind of thing, then you lose marks. So you're not double penalized, okay? Normally what I would do for something like this is an older question that was around, but what I would typically do, just have a second again, please. Right. So yes, well, what I normally would have done, especially with a class that have 100 people in here, is that I would ask, okay, do that. But then I would give you some characteristic equation here to work with. Oops. Yeah, I will give you a characteristic equation to work with now, so everybody starts off with the same thing. Right, so now we do have, if everybody was simplifying the thing incorrectly, and I have 50 different ones, I'll never finish correct the exam. So usually what I would do was that there would have been a part one to get the closed loop transfer function. A part two would have been, okay, assume the transfer function is so and so. Let me see you figure out the range that will drive it unstable. Yeah. So questions. All right, let me back here. So we're coming back to this. Yeah. Right. So back. So this sort of question is a similar type thing here. So you have it. In fact, it's the same thing that just redrawn. That one in the paper there. So you look at it now, and as you see, you solve the values of k that will drive the thing unstable. In this case, this one is asking you what range of values will drive it stable. So and you have 12 marks here. So your probably had 3 for simplifying the transfer function, 2 marks for getting the characteristic equation, and then several marks for completing each row of the router with stable, and then afterwards the answer for determining the value of k. All right. So questions. Right, there was a more complicated one in the December exam that we went through, and you have the solution, but everybody understands the technique, right? It's a straight sort of turn the crank, follow the method. You don't have to figure out too much. All you have to do is, in here, this particular one, you have a little bit of block diagram simplification here, and then you just simply follow the tabulation method. If in doing this question, when you tabulated it, you suddenly got a row where you had a 0 in the first cell and the other numbers are okay, then you have to use the things that we started off the class with. So in this row, you would replace this with an epsilon. If in doing the whole, in tabulating it out now, you suddenly got zeros in an entire row, then you have to use the second technique that we saw, which is to go to the row above and find the auxiliary polynomial and then complete the rest of the table. Right? In that case, you already know that the fact that you got a value of 0 here means that the system is already marginally stable or marginally unstable. Okay? But that's the kind of thing that the sort of questions that you could ask when you start to do ECNG 2009 later on. You're going to use this technique a lot, and particularly something called the root locus. The root locus technique and controls. Dr. Ramlal will carry you all through that. But the first part of it always is to use the Route-Hurwitz technique to figure out just what the system is doing. And then once you get the equations for k, then you now do another technique called the root locus technique, which allows you to see as k varies, if the pole started here as k varies, what sort of behavior does the roots follow? Right? Sometimes they follow these kind of behaviors where they do this and they as they vary k, but of course this will be a mirror image here, and do those kind of things. That tells you a lot about how to design systems, right? And you're going to spend a lot of time in the course doing things like that. But the basis for it is that you have to know this technique quite well. and he will assume that. So when he tells you, okay, that so and so is a characteristic equation, and from if you apply the Rauter-Hurwitz technique, that you get that K varies between this and this, that you have to understand now how to go about doing it. All right. Okay, so questions. Let me hear you. Make sense?
Yes, sir. No questions. I'm thinking already.
Right. Well, we have a lot of past papers to do. Yeah, you were saying something?
No, sir. No, sorry.
Yeah. Okay. Right. So a lot of this now, like everything else I've been telling you, listening to a class or looking at the lecture is one thing. You have to try it. You have to sit down with pen and paper or pencil and paper and try the question and see where you get stuck, or where you don't. Or if you're checking the answer against something that I have and you're not getting my answer, right? Maybe I'm tabulated incorrectly, or maybe there's an issue, but it's only if you do that, both you and I will know if there's an issue to address, okay? So you have the revision, I've told you the lectures here to look at. And you have the questions to try, both last time, the past papers that we have up, and this one as well. Yeah. So on Friday morning, we're going to look at this bit, which is the sort of last bit of the entire course revision that we have. There are a couple of things. One other thing I'll want to do with you all is to go over convolution. Just a bit to make sure everybody has that one. The biggest issue with convolution usually is people doing the AdMaths part of it, which is strange, but we'll review that. But we will have a look at lecture 22 and see if we get through that quickly enough, and then talk a little bit about convolution on Friday morning. Yeah? So if there are no other questions, if everybody is all right, I'll stop that. I'm hoping, as I said, you are keeping up with the work and so on. This is this second look at the work, of course, for you. And you have a lot of resources now compared to the first time, because we actually have the classes from last time that you could look at. You could go through this review as well. And of course, you have the past papers and hindsight. Right, so you have a lot more going for you. If you got stuck, we still have time here. So let me know and make sure we clarify any misunderstandings or misconceptions, so that the time when you get the exam, whenever in July or whenever it is, that you just sit down and just run through the exam very quickly, and you come out with a pass, a good, nice, healthy A in the course. Yeah.
So
yeah.
Excuse, yeah, so it wouldn't be able to tell us like approximately when exams would be, like if it would.
As soon as I find out, I'd let you all know. This summer school, typically when it ends, I believe the exams, maybe they may start the week after, at latest, right? So sorry, at earliest a week after, or at latest a week, 1 week further on, right? So before the middle of July, between the beginning of July, when after our semester ends, and about the middle of July is when all the exams will be. All right. So it's not going to be later than that. It's going to be fairly close to the end of the semester. But as soon as I get the time, well, funnily enough, you all tend to see the draft timetables even before I do. Right? I don't know how that happens, but someone when they publicize it for us and they tell us not to share it with the students already have it. Right? So you'll probably see the drafts at the same time that I do. Okay, but if not, as soon as I find out an approximate date, I'll let you all know. Okay? Yeah?
Yeah, thank you.
Okay. Okay, folks, so that's it for today's class. Thank you for attending. And as I said, as soon as the video is compiled and so on, I will upload it to YouTube so that you have it for your own revision as well. Okay. So take care, everyone, and I will see some of you all again in about an hour. Okay. Bye.